Hi all, this is Dr. Sapna, Assistant Professor, the Department of Electronics and Communication Engineering, KIT, Kalanya Karnanadi Institute of Technology, Coimbatore. Today we'll discuss about the transistor and how the signals are analyzed using a transistor. The main objective here is to understand how the transistor can act as an amplifier. So the main purpose of any transistor is basically the amplification of any input signal. Here we'll just consider about a electronic circuit, that is analog circuits, where we can process the analog input signals. So basically when we take about the our amplifiers, it can be a linear amplifiers. That is, linear indicates that whenever we have an input signal, the output will also be linearly proportional to the input signal. For example, if you are considering a audio system, or if you are somebody is singing a song, so the basic thing is that we have a microphone in which we have the signal to be taken, and this can be processed using an amplifier and then given as the speaker output. So here the main amplifier will consisting of basically the transistor circuit, which can be having a biased signal. The most commonly used transistor amplifiers are the configuration of common emitter. We know that there are different configuration for the transistors: common emitter, common base, and common collector. But common emitters are most commonly used as the amplifier circuits. Now we'll just see that whenever you have an amplifier or signal input, it will have both AC as well as DC components. So you can see that DC biasing, that is basically called as a large signal, and whenever you have a time varying signal, that is the AC, it is a small signal analysis. So we'll just discuss these both today. So here when you have AC and DC signals, you can consider that the two different types of amplifier analysis. So whenever we have this DC analysis to be performed, we can make the AC source to be 0. That is called as a large signal analysis of the transistor. Similarly, when we have to analyze the AC signal, we have to set the DC component or the DC sources to be 0. And this is called as a small signal analysis. This video will consider mainly on the large signal analysis, that is based on the DC components. So this DC components, we can consider that when we analyze this can give you mainly the operating point or the region where the transistor operates. So normally in the characteristics curve, if you consider that, we have always in the active region of the transistors. AC analysis, it is only the time varying signal source, and this can identify the other components of the transistor like gain as well as the impedances at input and output. Is a simple transistor amplifier circuit. So you can just see that you have some resistors connected to that, and it is of the common emitter configuration. So there is a resistor at the input side, which is your base side, and there is an output, which is the collector output, and there is a resistor at the collector terminal. Now you can also see that there are two inputs given to this. One is the biasing input and another is the analog AC inputs. Now the output, whenever we are considering this, you can just see that the relation between the Vi and VCC, that is the input and output voltage relations. There will be a cousin operating point, that is a point at which the transistor works properly, and that happens only in the active region. And when the input is changed, you can see that we have the saturation region as well as the cutoff region, which is below some value of your IB or VB, and similarly the cutoff region when it exceeds the biasing, when both are in the reverse bias conditions. And this diagram shows a clear indication of how various changes in the transistor analysis. So you can just see that it gives the VC versus IC, that is output current as well as the supply voltage variation. So VCC is the supply voltage, VC is the output voltage of the transistor between a collector and emitter, and IC is the collector current. Now when we have a line connecting the IC and VCE curve from two different sections, VCC by RC and VCC, will be able to get the load line analysis. So here we can just see that time varying input signal, whenever it is being given, it is being superimposed with the DC output, DC input voltage, and the output changes along with the component of the time varying output voltage. So if you are writing an equations at the input as well as output, you can see that it is based on the Kirchhoff law. So here Vs will be equal to, there is a supply voltage, it will be IB RB plus VB, and similarly at the output it is 0 will be equal to IC RC plus VC. So from this we'll be able to get the value of your input current as well as your output current. You can directly take the equations and calculate the value of the input current as well as the output current. So we also know that the transistor, when it is been mainly analyzed during the forward bias, that is input junction will be always forward biased, that is between your emitter and base, and collector to base terminal will be always reverse biased. So if you consider for a common emitter transistor, which is your basically used amplifier circuits, we can see that we have a forward biasing at the input, that is between your base and the emitter terminal, where emitter is grounded and base is acting as the input terminals. Now if you consider that it has got a same operation as that of the diode. So if you draw a graph between these, you can just see that VBE and IC, that is base to emitter voltage and the collector current. We can have a curve similar to that of your diode curves. So you can just replace this input side using a diode component. That is what is this one, that is the input terminal of your transistor. Between your base and emitter we can replace using a diode. So similar to the diode characteristics, we are able to get VBE and IC. And similarly at the output side also, if you are considering, you can see the collector current expression will be equal to IS, IC will be equal to IS into e power VBE by VT. It's also similar to your diode expressions. Now what is this? VBE is the input base voltage, and VT is our basic thermal voltage, and IS is the reverse saturation current. So the output side we can replace by the current source, and the input side will be able to replace by the diode. So this is the basic equivalent circuit of any large signal analysis. So this large signal analysis, when we consider, we can say that we are dealing with the biased supply voltage. So using the basic equations of the diodes itself, we can also calculate what will be the emitter current as well as your collector current. So here in this particular analysis, we'll replace the VB, that is you can change the VBE. With change in VBE, there's a significant change in the collector current, that is a small change in VBE itself can make a significant change in the collector current. Similarly, we can also make the VBE to be fixed, that is the input voltage to be fixed, and change the VCE, that is the output characteristics, VCE output voltage to output current. So for fixed VBE, we'll be able to get some constant or linear proportional output volt current. So you can just see that VCE can be varied with different values, and we'll be able to fix some VBE. So by changing the values of VCE, and see that it has been independent of the voltage, it depends upon only the input fixed voltages. So depending upon that, we can also say that it depends upon the IB currents. So the basic expression IS, which where it is the reverse saturation current, from this we can also calculate the collector current. So IC will be equal to IS into exponential VBE by VT. Similarly, we can also calculate what will be the input current. So what is our emitter current? From this basic thing, we know that the total input current that is your IE will be equal to the sum of the base current as well as the collector current, which is being given by the expression IE will be equal to IC plus IB. And we also know that the collector current will also be equal to beta IB. So using this expression we can write out what is the base current expression. So IB will be equal to IC divided by beta. So IC is the expression of IS into exponential VB by VT. So IB will be equal to 1 by beta into IS exponential of VB by VT. And similarly, IE will also, that is your emitter current can also be obtained using the same relations. That is IE will be equal to 1 plus beta divided by beta IS into e power VB by VT. So this is the basic equations which relates the change, that is your input to output currents. And depending upon the input voltage, you can say that is a large signal model, because this model is applicable for any change in the VB, that is it is independent of your VB voltage. It changes, whatever is the variation of your input VB changes will not have much changes in the output collector current. It mainly depends upon the base currents. So here when we consider this also has got a main significant effect on the value of your beta. Beta value, we know that it ranges in terms of 50 to 200. So it is very sensitive to beta values. So we can say that it is not stable. So we move on to the different biasing analysis. The first biasing is called as fixed biasing. So we'll also consider same like analysis use your circuits. Same thing can be used here also. So the first large signal analysis can be done by using some biasing of the transistor. That is a fixed bias. This is for the NPN transistor and this is for the PNP transistor. So we can differentiate with respect to the emitter arrowhead. So we know that the direction of current for the base and the collector is towards the transistor, and emitter will be away from the transistor. Now applying the Kirchhoff voltage law at the input as well as the output side, we'll be able to calculate what will be the collector current as well as the base current. So first we'll apply KVL to the input side. So to calculate the IB, you can just use the equation. What is the total loop equations? The total voltage across this will be equal to VBB will be equal to IB plus RB, that is a voltage across this resistor where we have a RB resistor, and the current flowing through this will be IB. So IB RB plus there is a small amount of voltage which is being present across the base and emitter, which will be equal to VBE. So VBB will be equal to IB RB plus VBE. Normally we can always neglect this VBE because it is very small. So or can also take in the form of 0.7 volts. And the collector current, you can say that IC will be equal to beta IB. So based on this equation, we will be able to calculate what will be IB as well as what will be the IC values. And at the output side, if you consider, you can say that the supply voltage VCC will be equal to collector current to the resistor, that is the voltage across this resistance IC into RC plus VCE, the voltage drop across this collector and emitter. So these are the two basic equations which correspond to the large signal analysis using the fixed bias. Now if VBB is very larger compared with your VBE and RB is also larger, then you can say that IB and IC are insensitive to the VBE, reduces the non-linearity functions. We know that always the transistor act as a non-linear condition. So we'll go for this non-linearity reductions. So fixed bias is very sensitive to this beta conditions. So we can also modify this biasing giving different values to the resistors across this collector as well as the feedback towards the collector to base. That is there are two more biasing sections we can discuss here. That is based on your collector to base bias or the feedback bias, or can say using the potential divider bias, which makes the linearity to be reduced. So here you can say there are two more feedback systems what we discussed here. So this first one, it is acting as a collector feedback biasing of the transistor, where the base resistor is being given from the collector. So there is a feedback taken from the collector, and that is being fed as the input to the base terminal. So the expression can change and will be able to get a better biasing control here. So the equations corresponding to this input side as well as output side, using those equations we'll be able to calculate what will be the collector current, what will be the base current, as well as what will be the emitter current. So here you can just see that. So what is your equation corresponding to this terminal? Vc will be equal to Vcc minus ICRC. So here both the resistance you can say that you will have your current. So IC whatever you are flowing, here it will be IC and here it will be IP. So the RC will be equal to VC will be equal to VCC minus ICRC minus IBRC. And similarly we can consider that your VB equal to VBE, and V can be considered to be 0 here. And the IB equation we can just calculate how Vc minus Vb, the voltage across this point divided by the resistor Rb. So IC also will be equal to beta into IB. So what is the IE from this? IE can be calculated as IC plus IB, which is also approximately equal to the same IC values. So your IC and IE will be almost similar. This is for the collector to feedback or collector to base bias, which can give a better stability. And the last one, it is the voltage divider bias. This is more stable compared with that of the collector feedback bias. So you can just see that we are using the potential divider rule. So the input base then coming from the collector, we are giving to the supply. So you are dividing the base voltage and base currents here. So we'll have to take a point here, and what will be the voltage across this point. Based on that you can divide. So if you are dividing in a proper way, you will be able to get the stability improvement here. So here in this circuit you can see across this terminal, that is Vc will be equal to Vcc minus ICRC. So we'll be able to get the voltage across the collector sections, and this will also be equal to VE plus VCE. This is also equal to this one. And similarly VE will be equal to IERE, that is the voltage across this one, it will be equal to IERE, that is the current across the resistor, emitter resistor. Yeah. So IERE will be equal to a VE, and that is also equal to this side, that is VB minus VBE. These both are equal. Similarly VCE, if you consider, it is VC minus VE, which is also equal to VCC minus ICRC plus IERE. Now at the input side, the voltage at this junction will be VB will be equal to VBE plus VE. Okay, this can also be across this resistor, that will be equal to VRB2. There are two resistors dividing the potential, that is RB1 and RB2. So the voltage at this point will be equal to, across this RB2, it will be equal to RB2 divided by RB1 plus RB2 into VCC. And the current across this IB, that is flowing across the resistor, flowing along the resistor R2 will be equal to IB2, which will be equal to VB divided by RB2. Similarly, the current flowing in this RB1 will be equal to IB plus IB2, which will be equal to VCC minus VB divided by RB1. And similarly, the total resistance across this will be equal to RB1 into RB2 divided by RB1 plus RB2. And similarly, the total IB current, the current flowing towards the base terminal will be equal to IB, and that will be equal to VB minus VBE divided by RB plus 1 plus beta RE. And similarly the collector current IC will be equal to beta IB. So we are able to calculate what will be the collector current, base current, and the emitter current also. So IE will be equal to IC plus IB. So it is also equal to a VE by RE. This also gives a very stable equations corresponding to the biasing. This forms the AC analysis. So this large scale analysis or the AC analysis, we can DC analysis, we can consider that we have a input which is basically the biased voltages. Whenever you have the DC biasing voltage, if you are analyzing that, that is considered as the large signal analysis. Thank you.